If the reaction is not possible at room temperature, so what we are going to do? We will raise the temperature. Arrhenius equation give rise to the significance of K and T. What is K? K is velocity constant, T is temperature. See, I am applying a minimum amount of energy to bring them close as well as they collide with each other. Every rise of 10 degrees centigrade, the rate or velocity of a chemical reaction gets doubled. Hello my dear students, I am Renuka Ashok, Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. My dear students, last session, that is in the fourth session of chapter Chemical Kinetics, I discussed about an overall view of zero order reaction as well as first order reaction, and I solved so many numericals which is by using integrated rate equation of zero order reaction as well as what first order reaction. Okay. Now, in this session, I am going to explain temperature dependence of the rate of reaction. That means how temperature influences the rate of chemical reaction as well as Arrhenius equation and activation energy, qualitative increases in reaction rate with temperature. Okay. Mainly this session, I am going to explain about the factor temperature, how it affects the velocity of a chemical reaction. If you want to increase the velocity of a chemical reaction or rate of a chemical reaction, you have to apply so many factors. In that, one of the factor is concentration, pressure, catalyst, nature of reactant, physical state of reactant, as well as the very important factor is what? Temperature. Today in this session, I am going to explain what is the effect of temperature on the rate of reaction, and one more thing, I am going to explain about one new equation. That equation is Arrhenius equation, and you heard about different types of energy like kinetic energy, potential energy, like that. But today in this class, I am going to explain one term that is known as what? Activation energy. Now, the temperature dependence of the rate of reaction. Okay. Now you know that as temperature increases, the velocity of a chemical reaction also increases. That one I can say temperature is directly proportional to rate or velocity of a chemical reaction. As temperature increases, the velocity or rate also increases. That's why in the practical class, if the reaction is not possible at room temperature, so what we are going to do? We will raise the temperature. So, for chemical reaction is significantly affected by a change in temperature. For most of the chemical reaction, the rate increases with increase in temperature. Rate increases with increases in temperature. Therefore, as temperature increases, the velocity of a chemical reaction also increases. That I can say the temperature and velocity are directly proportional to each other. For that, I'll give one example. For example, consider decomposition of nitrogen pentoxide. So, time taken for half of the original amount of material to decompose is 12 minutes. It will take 12 minutes at 50 degrees centigrade. 5 hours at 25 degrees centigrade. 10 days at 0 degree centigrade. See, it is 50 degree, it is 25 degree, it is 0 degree. If it is 50 degrees centigrade, the reaction is going to complete in only how many minutes? 12 minutes. If at 25 degrees centigrade, the reaction takes only 5 hours. So, if it is at 0 degree, it will take 10 days. Therefore, what does this example indicate? As temperature increases, the reactions also become fast. Therefore, one I can say the temperature increases, the velocity of a chemical reaction also increases. But from experimentally it is observed that just by rise of 10 degrees centigrade, just by rise of 10 degrees centigrade, for example, one reaction takes place at T Kelvin, I'll rise at 10 degrees centigrade. Therefore, the temperature is T become what? T plus 10. Okay, so what's the initial temperature? T Kelvin. I'll rise just 10 degrees centigrade. What happens by just rising 10 degrees centigrade? Andre velocities get doubled. Velocities gets doubled. Okay, so the rate usually becomes doubled for each 10 degree rise in temperature. My dear student, please remember this key point. Every rise of 10 degrees centigrade, the rate or velocity of a chemical reaction gets doubled. If it is V, it will become 2V just by rising 10 degree centigrade. Please remember this point. So once again, I'll repeat, my dear student, for every rise of 10 degree centigrade, the velocity or rate of a chemical reaction also gets doubled. From that, one you can going to give a definition for temperature coefficient. Temperature coefficient. Observe here, it is the ratio of velocity constant. It is the ratio of velocity constant at two different temperature. One is at T plus 10 Kelvin, another is at T Kelvin. So the ratio of velocity constant at two temperature which is differ by 10 degrees centigrade, that is called as what? Temperature coefficient. Okay, what is temperature coefficient? Once again, I'll repeat the definition. Temperature coefficient is the ratio of velocity constant. Velocity constant is denoted by K. So what's the initial temperature? Initial temperature is T Kelvin. What's the final temperature? T plus 10 Kelvin. I'm rising only how much of temperature? I'm rising only 10 degrees centigrade. By raising 10 degrees centigrade, what will happen to the rate of the reaction? The rate of the reaction gets doubled. Therefore, temperature coefficient is equal to the ratio of velocity constant at two different temperature which is differ by 10 degrees centigrade. Therefore, temperature coefficient is equal to Kt plus 10 divided by Kt. It is the ratio between velocity constants. At two different temperature differ by 10 degrees centigrade. So this value will become 2. Therefore, most of the reaction, the temperature coefficient value is 2, as well as the temperature coefficient lies between 2 to 3. So what's the value of temperature coefficient for most of the reaction? The temperature coefficient for most of the reaction lies between 2 to 3. Exactly, it is 2. Sometime it lies between what? 2 to 3. So therefore, the ratio of the specific rate constant of reaction at two different temperature differing by 10 degrees centigrade is known as temperature coefficient. What is temperature coefficient? Temperature coefficient is the ratio of specific rate constant of reaction at two different temperatures differing by 10 degrees centigrade is known as temperature coefficient. The rate usually becomes doubled for each 10 degree rise in temperature. Please, my dear student, I am repeating again and again, for every rise of 10 degrees centigrade, the velocity of a chemical reaction gets doubled. From this, what's the value of temperature coefficient? The value of temperature coefficient is 2, as well as it's also lies between 2 to 3. Therefore, what is the effect of temperature on the rate of the reaction? From this example, the decomposition of N2O5, as by decreasing the temperature, it is 50 degree, it is 25 degrees centigrade, it is 0 degrees centigrade, the time taken is also increases. If it is 50 degrees centigrade, the reaction is going to complete in 12 minutes, 25 degree take 5 hours, 0 degree it will take 10 days. From this example, one we can say for the most of the reaction, the velocity of a chemical reaction can be increased by increasing temperature. Therefore, velocity and temperature are directly proportional to each other. But if you want to double the velocity of a chemical reaction, you just rise 10 degree centigrade. So, this is an effect of temperature on the rate of reaction. Next, Arrhenius. According to Arrhenius, reaction rate constant K is directly proportional to e to the power of minus EA by RT. That is, Arrhenius equation gives relationship between, he gives a relationship between K and T. What is K? K is velocity constant. T is temperature. What is the significance of Arrhenius equation, my dear student? So Arrhenius equation gives the relationship between K and T. Arrhenius equation gives the relationship between K and T, and this is called as Arrhenius equation. 2 mark, very important question. 2 mark, very important question for your board. K is equal to A into e to the power of minus EA by RT. E to the power of minus EA by RT. What is Arrhenius equation? Arrhenius equation is K is equal to A into e to the power of minus EA by RT, where K is rate constant or velocity constant. Rate constant or what? Velocity constant. Rate constant or what? Velocity constant. A is called as Arrhenius constant or frequency factor. A is called as Arrhenius constant or frequency factor. R is universal gas constant. Universal gas constant. R is universal gas constant. Its value is 8.314 joule per Kelvin per mole. So what's the value of universal gas constant? Capital R is 8.314 joule per Kelvin per mole. But my dear student, the value of R is different units of what is the energy units. If energy is expressed in terms of calorie, the value of R is 2. Therefore, when energy is in joule, what's the value of R? 8.314. And T is temperature in Kelvin. EA is energy of activation or activation energy. Energy of activation or what? Activation energy. Therefore, the Arrhenius equation, once again I'll write K is equal to A into e to the power of minus EA by RT. This is called as Arrhenius equation. What is K? K is called as velocity constant. A is called as Arrhenius constant. E is called as Napier's base of logarithm. Napier base of logarithm. EA is energy of activation. EA is called as energy of activation or activation energy. T is temperature in Kelvin. R is universal gas constant. Therefore, Arrhenius equation, once again I am going to repeat, Arrhenius equation gives the relationship between K and T. So what is the significance of Arrhenius equation? Arrhenius equation gives rise to the significance of K and T. What is K? K is velocity constant, T is temperature. What is Arrhenius equation? Arrhenius equation is equal to K is equal to A into e to the power of minus EA by RT. What is K? K is velocity constant, A is Arrhenius constant or frequency factor, small e is Napier's base of logarithm, EA is activation energy, R is universal gas constant, and T is temperature in Kelvin. Here, new term which comes in Arrhenius equation is, let us consider R give rise to P. Before the formation of product, there is a formation of activated complex or transition state. This decomposes to give product. To form activated complex or transition state, it requires minimum energy. That minimum energy is called as what? Activation energy. My dear student, what is activation energy? The minimum amount of energy required by the reactants to form activated complex is called as activation energy. Activation energy is equal to threshold energy minus average energy possessed by the reactant molecules. How do you calculate activation energy? Activation energy is equal to threshold energy minus average energy possessed by the reactant molecule. What is threshold energy? Threshold energy is the minimum amount of energy by the reactant molecule must possess to form the product upon mutual collision is called as threshold energy. For example, if you consider these two are reactant, they must react with each other. The molecule of this reactant must collide with each other. See, these are the molecules of two reactant means they come closer as well as they collide with each other. See, I am applying a minimum amount of energy to bring them close as well as they collide with each other. This minimum amount of energy is called as what? Threshold energy. Therefore, what is threshold energy? The minimum amount of energy the reactant molecule must possess to form the product upon mutual collision is called as what? Threshold energy. Today, I introduce new terms in chemical kinetics chapter, that is activation energy as well as what? Threshold energy. What is activation energy? Activation energy is the energy required for the reactant molecule, energy required by reactant molecule to form activated complex. As I explained you, the reactants are not directly converted into product. Before formation of product, there is a formation of activated complex, or it is called as transition state. That they require the minimum amount of energy, that is called as what? Activation energy. And how reactants are converted into product? They undergo effective collisions. To get this mutual collision or effective collision, they require minimum amount of energy. That energy is called as what? Threshold energy. Therefore, activation energy is calculated by using formula. Activation energy is equal to threshold energy minus average energy possessed by the reactant molecules. Was the expression which is used to calculate activation energy. Activation energy is equal to threshold energy minus average energy possessed by the reactant molecules. Average energy possessed by the reactant molecules. Okay. So this about activation energy as well as what? Threshold energy. Now, I am going to explain this by taking an example of hydrogen reacts with iodine. It will form hydrogen iodide. All of you know that when hydrogen reacts with iodine, give rise to hydrogen iodide, and the reaction is represented as H2 plus I2 give rise to 2HI. But when hydrogen reacts with iodine, that does not form HI directly. In between, it will form intermediate, and here hydrogen iodine are partially bonded. Therefore, it is also called as what? Transition state. Also called as what? Transition state. So, according to Arrhenius, this reaction can take place only where a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. Okay. So, according to Arrhenius, hydrogen and iodine, they collide with each other. The collision takes place between the molecules of hydrogen as well as molecules of iodine to form an unstable intermediate. It decomposes to form, what is that? Hydrogen iodide. The energy required to form this intermediate, it is also called as what? Activated complex. It is also called as what? Activated complex. That is called as what? Activation energy. Therefore, 1 mark, very important question, my children. The energy required to form intermediate or activated complex is known as what? Activation energy. And it is denoted by EA. Capital E subscript small a indicates activation energy. Now, I am going to show this by using graphical method. Let us consider along y-axis you take potential energy as well as along x-axis you take reaction coordinate. What is reaction coordinate? Reaction coordinate is a energy profile which shows how energy exchange takes place when reactants are converted into product. Therefore, this diagram is also called as energy profile diagram. It is also called as energy profile diagram. So, what is reaction coordinate? Reaction coordinate shows the how energy changes, whether heat is liberated or heat is absorbed when the reactants are converted into product. That profile, that energy change is called as what? Reaction coordinate. When I plot a graph of potential energy versus reaction coordinate, I'll get one graph that is called as energy hill or energy barrier. Energy hill or energy barrier. Energy hill or what? Energy barrier. This energy hill or energy barrier, you should not touch x-axis as well as what? Y-axis, as well as should not passes through the origin. So, this height of the hill is called as activation energy. Height of the hill is called as activation energy. At this peak, there is a formation of activated complex, and here it is energy is called as threshold energy. As the gap between this foot to here end, this gap is delta H. This gap is delta H. So, what's the graph plotted? Graph is plotted potential energy versus reaction coordinate. Potential energy versus reaction coordinate. A graph of potential energy versus reaction coordinate, you will get energy hill or energy barrier. So, according to Arrhenius, when any reactant or react, that does not give rise to product, in between they will give intermediate. That intermediate is called as activated complex or transition state. It is unstable. Hence, it decomposes to form product. To form transition state or to form activated complex, it requires energy. That energy is called as what? Activation energy, and it is denoted by EA. Now, qualitative increase of reaction rate with temperature. Now, I'll explain how does temperature influences the reaction rate. Now, when you consider any gas, it is made up of so many number of molecules, lots of molecules. All the molecules in the reacting species do not have the same kinetic energy. You know that molecules, if you consider 1 mole of gas, it contains Avogadro number of molecules, that is 6.022 into 10 to the power of 23 molecule. The energy of one molecule not same as that of the energy of the other molecule. Then you consider the human beings also. So, energy of one person is not same as that of the energy of other person. So, similarly, molecule does not have same energy. Each molecule possesses different energy. All the molecules in the reacting species do not have the same kinetic energy. Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by the plotting the fraction of molecules Ne by Nt. Fraction of molecules means what? Ne by Nt with kinetic energy. Along y-axis, you take Ne by Nt. Along x-axis, you take kinetic energy. Along y-axis, you take Ne by Nt. Along x-axis, you take kinetic energy. What is Ne? Ne is the number of molecules with energy E. Nt is the total number of molecule. What is Ne? Ne is the number of molecules with energy E. Nt is the total number of molecule. So, when you plot a graph, you will get graph like this. Okay. So, this height, the peak of the curve, it is called as what? Most probable kinetic energy. Here, it is called as what? Most probable kinetic energy. This most probable, that is kinetic energy of maximum fraction of molecule. What is most probable kinetic energy? Kinetic energy of maximum fraction of molecule. So, now in chemical kinetics, this is the third graph. First graph I plotted for, in case of integrated rate equation, I plotted for zero order as well as first order, concentration versus time. Second graph graph to explain the effect of catalyst. I plotted a graph of potential energy versus what? Reaction coordinate. Potential energy versus what? Reaction coordinate. To explain the effect of temperature, now I am plotting the fraction of molecule. What is fraction of molecule? Fraction of molecule is Ne by NT. Ne by NT. What is Ne? Ne is the number of molecules with energy E. NT is the total number of molecule. NT is the total number of molecule versus kinetic energy. So this is the peak is called as most probable kinetic energy. What is most probable kinetic energy? Kinetic energy of maximum fraction of molecule. What is most probable kinetic energy? Kinetic energy of maximum fraction of molecule. What is Ne? Ne is the number of molecules we having energy E. What is NT? NT is the total number of molecules. NT is the total number of molecules. Okay. Now, to explain the effect of temperature on the rate of reaction, now I am going to use this graph. Fraction of molecules means Ne by NT. Ne by NT. Along y-axis, I am going to take Ne by NT. Ne by NT. Along x-axis, I am going to take kinetic energy. As the temperature increases from T to T plus 10 Kelvin, T Kelvin to T plus 10 Kelvin, the fraction of molecules having kinetic energy greater than activation energy increase, thus effective collision, and hence the rate of reaction increases. So what happens just by rising 10 degrees centigrade? See here, it's activation energy. So having kinetic energy is greater than activation energy. Very important point is which type of collisions are increases? Effective collisions are going to increase. From the graph, observe that. Now I'll plot a graph for, this is for T Kelvin. This is for T plus 10 Kelvin, second graph. This first graph is for. Now observe this area, this is what I am shading here. This area is shows the fraction of molecule reacting at what? T Kelvin. And this area, so which shows the fraction of molecules which reacting at T plus 10 Kelvin. Observing, but rising 10 degrees centigrade temperature increase in the number of activated molecules. Whatever activated molecules here, the fraction of molecule which get doubled. So as number of active molecules get doubled from the graph, number of effective collisions also increase as well as increase in the rate. Therefore, my dear student, when you take a graph of Ne by NT versus kinetic energy. So first graph, this is we're going to get for T Kelvin. Second graph, we're going to get for T plus 10 Kelvin. Okay, this area at T Kelvin, activated molecules at T Kelvin. This shaded part, what I am shading here, so this is at what? T plus 10 Kelvin. Observe from the graph, as 10 degrees centigrade, the number of activated molecules at T Kelvin is get doubled. As number of activated molecules get doubled, number of effective collisions also increases as well as velocity increases. Therefore, for every rise of 10 degrees centigrade, the number of activated molecules increases as well as its activation increases. Therefore, its velocity also increases. Therefore, my student, for every rise of 10 degrees centigrade, so the velocity gets doubled. What is the effect of temperature on the rate of reaction is explained by using graph. That graph is Ne by NT. Ne by NT. It is called as what? Fraction of molecules. Ne by NT is nothing but what? Fraction of molecules versus kinetic energy, where Ne is the number of molecules having energy E, NT is the total number of molecules. This graph shows at T Kelvin. Second graph shows at T plus 10 Kelvin. Now, same qualitative increase in reaction rate with temperature, it can be shown by graphical method. In the Arrhenius equation, factor e to the power of minus Ea by RT corresponds to the fraction of molecules that have kinetic energy greater than Ea. Okay, minus E to the power of minus e to the power of minus Ea by RT, that indicate the fraction of molecules that have kinetic energy greater than Ea. Taking natural logarithm of both sides to the equation, log natural K is equal to minus Ea by RT plus log natural A. Plot of log natural, if I compare with this reaction equation with y is equal to mx plus c, in place of y we have log natural k, in place of x we have 1 by t, in place of c you have log natural a, as well as slope m is equal to minus Ea by r, with slope negative, therefore we will get a straight line which are sloping downward. So what we have to plot? Log natural k versus 1 by t, log natural versus 1 by t, we will get with y-intercept log natural a, and slope is minus Ea by r, slope is equal to minus Ea by r, therefore Ea is equal to minus slope into r, minus slope into r. This is the graphical method. By measuring the slope of the line, the activation energy Ea can be calculated. Therefore, by graphical method, how can you calculate Ea? Ea is equal to, what's the formula I deduced from the graph? Ea is equal to minus slope. Ea is equal to minus slope into r. Ea is equal to minus slope into r. What is r? R is universal gas constant. We have to plot a graph of log natural k versus 1 by t. Log natural k versus 1 by t. The first graph in this chapter, concentration versus time. First graph in this chapter, concentration versus time. Second graph in this chapter, potential energy versus reaction coordinate. Potential energy versus reaction coordinate. Third graph in this chapter, Ne by Nt versus kinetic energy. Ne by Nt versus kinetic energy. Fourth graph in this chapter, log natural k versus 1 by. Now, rate constant method. Now we have formula log natural k is equal to minus Ea by RT plus log natural A. This is a equation by taking log natural on both sides. Now I am going to consider this equation at two temperature T1 and T2. When temperature T1, velocity constant become K1. When temperature T2, velocity constant become K2. Therefore, first equation is at T1, log natural K1 is equal to minus Ea by RT1 plus log natural A. At temperature T2, log natural K2 is equal to minus Ea by RT2 plus log natural A. This is equation 1 and equation 2. Since A is constant for a given reaction, K1 and K2 are the values of rate constant, temperature T1 and T2. Subtracting equation 2 from 1, okay? 2 minus 1, equation 2 minus 1. So 2 minus 1 means what happens? Log natural K2 minus log natural K1. Log natural A gets cancelled. 2 minus 1. So minus Ea RT1 minus of minus Ea RT1. Therefore, you know that log natural A minus log natural B is nothing but log natural A by B. Here also, log natural K2 minus log natural K1, it is nothing but log natural K2 by K1. I'll take Ea as a common factor and R also common factor. Ea by R as a common factor, it will become 1 by T1 minus 1 by T2. Now I am going to convert this log natural to log to the base 10. You have to multiply by 2.303. I am simplifying this. So it will become what? T2 minus T1 divided by T1 and T2. Therefore, what's the final expression for at 2 temperature? Arrhenius equation at 2 temperature T1 and what? T2 log K2 by K1 to the base 10, log K2 by K1 to the base 10, Ea by 2.303 R, Ea by 2.303 R, T2 minus T1 divided by T2 T1, T2 minus T1 divided by T2 T1. This is an Arrhenius equation at 2 temperature T1 and T2. Please, I'll repeat once again, my dear student, I'm repeating this equation. Log K2 by K1 to the base 10 is equal to EA by 2.303 R into T2 minus T1 divided by T2 T1. So this is an expression of Arrhenius equation at two temperature T1 and T2 and two velocity constants K1 and K2. On this you have numericals. Okay, they'll give two temperatures T1 and T2 as well as they'll give two velocity constants K1 and K2. From that, you have to find out activation energy. From this, you have to find out activation energy. So, what I discussed, my dear student, in this class, I discussed about two graphs. One is related with catalyst, another one related with temperature. Related with catalyst, I discussed graph that is potential energy versus what? Reaction coordinate. Related with temperature, I discussed one graph that is fraction of molecules, that is Ne by Nt versus kinetic energy, and I had given two equation, Arrhenius equation and temperature. One temperature T, K is equal to A into E to the power of minus EA by RT. At two temperature T1 and T2, log K2 by K1 is equal to EA by 2.303 R T2 minus T1 divided by T2 T1. Okay. Next session, I'll come up with effect of catalyst and collision theory of chemical reaction. This is the last session of this chapter, that is session 6 of this chapter, the chemical kinetics. Okay, so next session I'll come up with collision theory as well as what is the effect of catalyst on the rate of reaction as well as numerical. Thank you. Goodbye.